That's the thing. I was like, I see.
Oh, thank you. Did you guys have a good weekend? I will clean the board.
Wait, that could be kind of cool, actually.
Bro, you never seen the Bible?
Yeah, there's an adventure Bible.
Yeah, it's
Yeah,
so
really?
Yeah.
You know, Paul drew it back
So, I will begin with a word of prayer here in a second to have everybody's attention. I guess Dr. Sprano didn't have too much to cover this morning from the look of it. This board is kind of sparse. I'll begin. Dear Heavenly Father, we thank you for the weekend just completed, for the time to relax and refresh. Just pray to be with us today. Help us to glorify you, what we do, and just understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. All right, so here's the attendance sheet. I guess I'll start class with an interesting calculation that you should all see. So example 1. All right. Let's look at x, well, let's say z equal to I times theta. What happens if we square this? I theta, right? Which of course is I squared theta squared, which is minus theta squared, right? And z cubed is I cubed theta cubed, right? Which is actually minus I theta cubed. If we calculate z to the power 4, we get I to the 4th, theta to the 4th, which is actually, well, theta to the 4th. So here, I is our notation for the square root of minus 1 in the sense that I squared is equal to minus 1. Now, if you're in electrical engineering, you guys, for some reason, want to use I as current, and so then you use J for the square root of minus 1, and you have J squared as minus 1, you know. So this is the usual electrical engineering notation for this, right? But in mathematics, we use I for the imaginary number, imaginary unit I. So what happens with z to the 5th? You get I theta to the 5th, right? Anyway, so if you you sort through the pattern here, what you've got is that z to a, the odd power, 2k plus 1, is equal to minus 1 to the k times theta to the 2k plus 1, I believe. Do you guys see that pattern? So like, this is k equals to 0. This is k equals to 1. The fifth order is k equals to 2. On the other hand, if we have z to an even power, we've got minus 1 to the k times theta to the 2k. All right? So like, this would be, k equals 1. Here's k equals to 2. Here's k equals to 3 for this one. And this would be k equals to 1, k equals to 2, for this one down here. Next up, you'd have z to the 6th, which is minus, right? The next one is z to the sixth is equal to I to the sixth, theta to the sixth. But the key idea here is that I to the fourth is equal to what? I to the fourth is equal to 1. So basically, when you have I to the sixth, it simplifies to I squared, but I squared is minus 1, so you get minus theta to the sixth, right? So anyway, that's k equals to 2 for this formula. So do you guys follow me so far? I mean, just, yep.
Wait, how was the first one at k equals 1 for not? Because if you do...
Did I say k equals 1? Oh man, I meant 0. Yeah, sorry about that. You are correct. My bad. Was the other question about that too? Yeah.
I'm interested, how do you get a complex term out of that z to the 2k plus 1 formula? So for instance,
Oh yeah, I'm missing something. What am I missing? Yeah, there's an I here. Thank you. Very good. You're right. It was missing. Thank you. But the point is, it's either I or nothing. I mean, you can everything else you can either it's either a real number or it simplifies to plus or minus I, right? I mean that's okay. So put this all together. What you got? Well, check this out. So if we have e to the z, right? And we write that as the sum, n equals 0 to infinity of 1 over n factorial z to the n, right? So if we assume that if we take the exponential of an imaginary number, it works just the same, then what happens? You can break this into two pieces, right? The even pieces and the odd pieces. And what happens? Those simplify nicely, right? As I was just trying to expose you to, and you guys corrected my mistakes. So what we're looking at then is the sum k equals 0 to infinity of 1 over 2k parentheses factorial theta to the 2k. I missed something. What am I miss? What else is in here? Not the I. This is the even part, right? So z to the 2k is minus 1 to the k, so I don't forget my minus 1 to the k. And then I'll factor out the I on the other one. And what you've got is you've got the sum k equals 0 to infinity minus 1 to the k divided by 2k plus 1 factorial theta to the 2k plus 1. So here I've used the red part. And over here I've used the blue part. So what do we have? So this e to the z was actually e to the I theta, right? I just let z equal I theta for the sake of discussion. We have e to the I theta equals to what then? What's the first series? Yeah, the first term is, these are even, right? Even powers, even function. The even trigonometric function is cosine. This is straight up cosine, the Maclaurin series for cosine. And then you've got I. And this right here is the Maclaurin series for sine. And what you're looking at is known as Euler's identity. Now, I told you guys about this earlier in the semester, right? As a means to deriving trig identities. But now here's one way you could derive this formula. See, if you understand sine and cosine in terms of their power series, it's a natural thing to look at what happens if we try to look at an imaginary number and do the same thing. Well, if you do that, you naturally find yourself back to sine and cosine like this. So from another perspective, you could use what I've written as this is essentially the definition of the exponential. And some people do. There's about 5 competing definitions for the exponential. This is one of them. Do you guys have any questions about homework before I go on? Yep.
104. It gives a function and it says to find the 100 times derivative. But that's a 0.
Yeah, so this is essentially like the last problem on the quiz. So for problem 104, so here's what you want to do. You want to find all terms that contribute to the coefficient of x to the 100, then identify, so whatever that is, let's say that, whatever is this stuff, whatever you have, next to x to the 100, well, that has to be equal to, you have to have the 100th derivative evaluated at 0 over 100 factorial is equal to that stuff. So then you can figure out what the derivative is from that. So that's basically what you want to do for that problem. Now, that problem you've got, well, let me write down something similar to it. So similar, something like, I don't know, x plus x squared plus x cubed times cosine of x squared, plus 1 over 1 minus x cubed, You could have something like this and ask the question, what's the 100th derivative? So then you have to think about what are potential ways, how can I get a Maclaurin term with x to the 100, right? So the way I would basically look at it this way. This is x plus x squared plus x cubed. What's the Maclaurin series for cosine of x squared? Well, that's the sum. N equals 0 to infinity minus 1 to the n over 2n parentheses factorial. And then I have x to the x squared to the 2n, right? So I've got x to the 4n for this guy. And then over here, I've got the sum, let me use a different letter. J equals 0 to infinity of x to the 3j f of x. So here I'm using the geometric series, identifying that the radius is equal to x cubed. So if I have r to the power j, here. And also I'm making a u equals x squared substitution, so I've got u to the 2n, which is x squared to the 2n, which is x to the 4n. So there's my internal thinking for this step, right? And then I think about how can I obtain 100th power from these expressions, right? Like, where is x to the 100 appearing in this at all, if at all? So for my made-up example, is x to the 100 power in here? It's not, right? It skips right past it. You go x to the 99, x to the 102, right? So there is no 100 power in here. Irrelevant. Much like this marker. Ah! Whoa. What was that? Anyway, how about over here? Well, now we got to be more careful, right? Let's think about this. X times powers of 4. Does that get you to 100? It does not, right? Is there 100 power in here? Yes, there is, right? N equals to 25 gets me x to the 100 there. But is that relevant? Well, it's not, because I don't have a constant out here. So let's see here. if I'm multiplying x squared times this, how can I get to x to the 100? Let's think about it. I need either x to the 98 for this one, because x squared times an x to the 98 would give me x to the 100, or I would need a x to the 97 from this one, right? And can I get 98 or 97 from a multiple of 4? I can't, right? 96, then 100. Those are multiples of 4 in the neighborhood of what we're looking for. So the answer to this is 0. There is no x to the 100 term. Now that wasn't very satisfying. Would you guys like me to look at a derivative that works out non-trivially?
I have a question.
Yep.
Why can't you factor out an x, put it in the sum of the series of cosine, which would make it x to the 5n, no, x to the 4n plus the 1.
Well, I could do that, but then I'd have to write 3 other series. I mean, you could absolutely do that, but you'd have to be, you'd have 3 things to look at, right? You have the sum n equals 0 to infinity of minus 1 to the n over 2n plus 2n factorial, right? And I could write 3 series, but tell you what, I'll do it like this. Well, I think I'd have this, and then I'd have plus. I mean, I think you could do what I was about to write, but I'm a little bit apprehensive because I know that assuming power series calculation hold for non-power series is problematic. So but your suggestion, Riley, is going to be, it's not bad. I mean, it may be helpful to us in what the rest of the work we do here. I mean, you can do that, sure. I just sometimes don't because I can just think about what I'm interested in. If I can make the case from what I've already written, why write more? That's all. Now, so suppose so initial question posed, 0 is the answer because there is no such term. How about if we look for the, 99th derivative? Well then, you notice that this does not have anything of the form x to the 99, right? Am I right or wrong about that? You're going 96 plus 1 or 101. Miss 99, right? Here, when you get to n equals to 24, you get 96 plus 2, which is 98, and then you go to 102. This guy, hey, wait a minute. This one goes 96 plus, hey, this has got a 99 in it, doesn't it? For n equals to 24. So, aha. So for the 99th derivative, if I want to get x to the 99, I can take n equals to 24 gives me x to the 99. And here, j equals to 33 gives me x to the 99, right? Is there any other term which has x to the 99? I mean, that's it, right, for this one I made up. So I can cipher from this that I have minus 1 to the 24 over, let's see here, 48 factorial. Plus what? The coefficient on this one is kind of boring. Plus 1, right? Times x to the 99 plus stuff, right? So like my point is, this is the, when we look at the Maclaurin series for f of x, we have a bunch of stuff. We have this for the 99th power, and then it goes on, right? So you can equate that to f of 0 plus da-da-da. Eventually you get to the 99th power over 0 times 99 factorial, x to the 99, and then plus stuff, right? So then you can equate the coefficients of 2 power series term by term. And so what we have is that the 99th derivative evaluated at 0 divided by 99 factorial is equal to 1 plus 1 over 48 factorial. I don't recommend trying to put this into your calculator. You definitely have to work this problem symbolically, even though it's about a specific number, right? The numbers are too big for your calculator to hack. I mean, like, I think mine stopped at like around the 50 factorial mark. It certainly can't do arithmetic with it, like division. No. Anyway, so this will tell you then that the 99th derivative at 0 for the function is in fact 99 factorial times 1 plus 1 over 48 factorial for this problem. So that's the method. You just look for all possible ways that you can get the power you're interested in. Add those things together. That has to be equal to the derivative divided by that factorial power, whatever you're looking at, yeah.
Instead of splitting the series apart, could you have done it with the first one? You had n equals 24 and use the x of 3.
Well, yes, like, but you know, you can go back to the way I was doing it before Riley asked a question and just look at this and go, okay, so that's 96, and then only this one matters, right? And then you can look at 25, 100, well, that's too far. I mean, yeah, you can do, there are other ways to denote the work, but we should all agree that those are the terms that contribute to the 99 power, and those are the only ones, right? So that's essentially how you do 104. All right, let me do another problem here. So if I can get my computer to wake up here. Oop. All right, I don't think I've top hatted on this thing before. Let's see what happens. Hopefully it'll let me. Search for your school. All right, fine. Liberty University, yes. Log in with school account. What class are we today? 132. 1117. One 117 is the one. Ah! Getting away from me. So I wanted to spend a few more class minutes, a little bit more class time doing division of series, because I don't think I've done enough of that yet. I mean, we've done just a sprinkling of it. It would be good for us to do a little bit more of that. Because when I was in your place and somebody showed it to me quickly and then I walked away from it, I was like, what did they do? How many terms did you write? Like, it was confusing to me personally, so I can only assume that you guys suffer a similar fate, perhaps. But the thing that confused me about it to start with is, like, how much of the series do I have to write? And the answer basically to that is just try something and just be situationally aware that if you should make sure you have all the terms that you're looking at, essentially. Let's see if I can find what I'm looking for here. So I wrote some more notes for you guys, and I haven't posted them yet, but I will sometime soon. Not too much more. Don't worry. I pretty much posted everything. I still need to write the abstract for this article. It's kind of sad at the moment. Let's see here. But so I went ahead and typed up the things I wrote on the board last week about, like, the product of series, and I typed up the the proof that the exponent e to the x times e to the y is e to the x plus y, that thing we did, right? That silly, math prank of 1 minus x times 1 plus x squared works out to 1, right? That one, I did that one. But then I did something else a little bit different, which I don't want to write in the board, but I just want to like tell you about. And then what I want to do is I want to show you this way of thinking. This is a good way of thinking, and so I want you to know about it. But at the same time, I want to solve the problem that I have next as an example using long division instead. And I'll just tell you, I'm too lazy to type up the long division. Like long division to like put into this format for me at the moment, I just don't have a good notation. Somebody probably already has like a built-in thing for it, but let's just talk about the problem. So the problem is this. You have you're given a power series, all right? Let's say a Maclaurin series, just for the sake of, like everything I'm saying would equally well apply to a series not centered at 0, but just for the sake of notational like brevity, let's assume it's centered at 0, okay? So I'm looking for, if I have a series, can I find another series such that the product of them is 1? This is just like another way of saying, can I find the reciprocal series for a given series, right? This is the question I'm asking. And so to find the reciprocal series is tantamount to finding a series such that you multiply the given series by that new series and get 1, right? But because we multiply series order by order, that gives us all kinds of equations at each order for the coefficients that we don't know in terms of the coefficients we do know. We do know we're given the a sub 1, a sub 0, a sub 1, a sub 2, dot, dot, dot. What I don't know is the b sub 0, b sub 1, b sub 2, dot, 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 dot. All right? So I multiply this out. Here's the 0th order, the 1st order, the 2nd order, the 3rd order, you know, so forth and so on. And so you get an equation from each order. Like at 0th order, I get that a product of a0 and b0 has to be equal to 1 because that's the constant terms on the right-hand side. What are the terms next to x on the right-hand side? Trick question, right? There are none, right? So 0. 0 is the coefficient of x on the right-hand side. 0 is the coefficient of x squared on the right-hand side, and so forth and so on. So I get a0 b0 equal to 1. I get a0 b1 plus a1 b0 equal to 0. All right? And then I get all this junk equal to 0, and then all of that junk equal to 0. So if you look at it, we've got this infinite sequence of equations that we have to solve. We're trying to solve for the b's in terms of the a's, all right? So the first one's really easy to solve. How do you solve for b0? Well, divide, right? And then the second one, this one here, a0 b1 plus a1 b0, how do you solve that? Well, solve for b1, right? b1 is minus a1 b0 divided by a0. And then the thing is, I already found b0 from the previous step, right? So I plug that into here, and I get minus a1 over a0 squared, and that gives me b1. Well, this is starting to look good. I've got the formula for the first one. I've got the formula for the 0th one. I've got the formula for the first one. And maybe I can keep doing this, right? So yeah, I can keep doing this. At quadratic order, I'm solving this equation. If I solve for b2, I get minus a1 b1 minus a2 b0 over a0. Then I'll plug in this equation and that equation, and it gives me this formula for b2. And there's kind of a pattern here. You notice like there's always kind of like one more thing on the bottom there is on top, and every term. That pattern continues. Then the cubic term is this, and then I plug in. And this point, now we start getting different terms that combine together to give us like terms. It's getting more complicated. b3 is minus a1 cubed divided by a0 to the 4th, like so, right? And at this point, I'm tired of typing, so I stop there. But you could see that if you were so inclined, you could go on, right? There's a straightforward pattern here. You could derive the formula for the inverse of another series in terms of the coefficients of the 1, if you wanted to. And so I went ahead and I applied these toys I just built to the cosine series, right? So 1 over cosine is what? It is, so my a0 is 1, right? What's a1 in this cosine series? See, there is no x term, right? So a sub 1 is 0. Just like a sub 3 is 0, a sub 5 is 0, a sub 7 is 0, a sub 9 is 0. We could be here all day. Cosine is an even function. It has no odd terms in its Maclaurin expansion. So I give a sub 0 is 1, a sub 2 is minus 1/2, a sub 3 is 0. So up to the order that I've calculated, which is just cubic, I can see that I've got just this term and that term contributing. And notice that a1 is 0, so this just becomes minus a2 over a naught squared. A naught is 1 in this context, so it's just minus a2, which means this minus a half turned to a plus half, and that's it, right? So if you're so inclined, you could use my stupid formulas to calculate the inverse of a Maclaurin series to third order, you know. But this won't be any help to you, right, for a lot of examples, because a lot of examples that I invent end up being like 20th order, even though they're not that complicated. But I said in the notes that I would work this out in lecture using long division, so hey, let's do that. All right, so we're gonna divide 1 by the cosine series, all right? So what example is this? Example 3, is it maybe? Kind of, sort of. So let's do 1 over cosine x. So cosine x is what? It is 1 minus 1/2 x squared plus 1 over 24 x to the 4th. Did I do this I might have done this last time. I did something awful lot. Like it's in the mission. Uh-oh. Oh. So why did you say that? So here we're dividing it into 1. Cosine x is over here. It's okay. I mean, you already turned it in, that part? Okay. Like this, right? So how do you get a 1 here? Well, put a 1. So then we've got 1 minus 1/2 x squared. You subtract, what happens? You get 1/2 x squared minus 1 over 24 x to the 4th. So how do I get a 1/2 x squared from, I have to do what? Plus 1/2 x squared. And so that gives me 1/2 x squared minus 1/4 x to the 4th plus stuff. I mean, at this point, we've already recovered as far as my silly formulas went, right? Because my silly formulas are very limited. They only go to third order. And there is no third order term from just general even odd considerations here. And so you get 5/24. X to the 4th is the next term here. And then, of course, so I would put plus 5/24. X to the 4th is my next term, right? And then, I mean, that's enough. So the point is, using long division, oh man, computer, how dare you. I didn't give you permission to, there we go. Yeah, so there it is. This is the Maclaurin series, the 4th order for cosine, just like that. Again, I'll be posting these notes here hopefully a little bit later today. So I decided to go on and try on, yep, sir.
Those are also the first 3 non-trivial terms of that equation, right?
Well, yeah, what I mean by boxing that in is that 1 over cosine x is equal to 1 plus 1/2 x squared plus 5 over 24 x to the 4th. Fun fact, what is the 4th derivative of 0 if I let f of x equals to 1 over cosine x? Well, the 4th derivative divided by 4 factorial apparently would be 5 over 24, right? Because that's the coefficient right here next to x to the 4th. So this would tell me that the fourth derivative at 0 for this function is in fact equal to 5. So just to give you a little bit less intimidating example of this idea, right, that x to the 100 power is kind of a bit much, isn't it? But so we can use Taylor's theorem in conjunction with our other methods to find derivatives. This is a weird kind of backwards thinking, but it's interesting nonetheless. How about another example, tangent x? How would we find the power series, the Maclaurin series for tangent? Well, tangent sine over cosine, right? So if I call the unknown series b0, b1, b2, b3, x cubed, so forth. So my theme for today is basically to invent a notation for the series you don't know as a means of breaking down the algebra step by step. This is a potential method of calculation, all right? That's kind of the new thing I'm sharing with you today, if you're wondering. Like, what's different? That's the different thing. Is before I wasn't suggesting we give a name to the coefficients we don't know and work it out, right? I don't think we've done that before today. We've done many other things, but not that, I don't think. And at least not that I remember. So if this is the case, then that means that the sine series times, well, cosine times the unknown series has to be equal to the sine series, right? So we can do the same thing I did in the previous example, but now, instead of just having all zeros, I have interesting terms because sine has interesting coefficients, right? I've got like, well, there's no constant term this time, right? And so like the constant term on the left-hand side is 0. What's the constant term on the right-hand side? It's coming from b0 times 1, right? So I get b0. Apparently b0 is 0. Woohoo! Now how about linear? How about powers of x? Well, there's a coefficient of 1 over here, so I put a 1 here, right? How can I get an x from over here? Well, b0 times that won't work, right? Because that even powers. But b1x times this gives me, well, b1 times 1x. That gives me an x term, so I get b1. And that's the only way to get an x. See, because this is x squared, and you can't undo it, right? How about x squared? Well, there's 0 here. On the other side, you've got b0 times minus 1/2 times, and also the b2 times 1. And so you see what I'm doing? I'm just collecting all of the terms that come at each order. So like order 3, I've got minus 1/6 on the left-hand side. On the right-hand side, I've got b0 times, oh no, I don't have that, b1 times the 120 minus 1/2. That gives me order 3. And also, of course, b3 times 1 gives me order 3. And I think that's it. Yeah, I've got the 2 terms at order 3. But without me talking, oh, come on, seriously? I got to adjust the power settings on this thing. I don't know how. Error. I don't know. Whatever. Okay, so I've got equations to solve, and I can solve them basically top down. And when I do that, I get 0 for 0, 1 for 1, 0 for 2. This is not surprising, right? Tangent is a what? Is an odd function. I already know that the even terms in the Maclaurin series are all going to be trivial because of that general theorem we have. Even functions have even Maclaurin series. Odd functions have odd Maclaurin series, right? So b3, on the other hand, is 1/2 minus 1/6, which is 1/3, and b5 is this. And so here you go. Tangent of x is x plus 1/3 x cubed plus 2 to 15th x to the 5th plus dot, 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 right? Now, I don't think this is the right way to do things, all right? I'm illustrating this to illustrate a method, and a method of calculation. But for this specific example, there's a better way to find the power series. How would you do it? You would use long division. All right, we can do long division for this one more easily. See, because tangent x, like we said at the start, is sine x over cosine x, right? So all we do is we put the power series for sine in here, which is what? X minus 1/6 x cubed plus 1 over 120 x to the 5th. All right, I'll do it to order 5 this time. What's the power series for cosine? It is 1 minus 1/2 x squared plus 1 over 24 x to the 4th plus dot 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 dot, right? This is much easier than that, I think. What's my first term? What do I have to put here? I need to put an x, right? So I've got x. And then I do x times this. That gives me x minus 1/2 x cubed plus 1 over 24 x to the 5th plus dot 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 dot. Now I have to subtract, right? And so I get minus 1/6 plus 3/6, which is 1/3 x cubed. 1 minus 5 is minus 4 over 120, which is, I think that's minus 1 over 32. But I should probably check that with my calculator. Give me a second here. Oh, 1/30th, my bad. Duh. Then what comes next? Well, you see it, right? How do I get 1/3 x cubed from this? These are kind of stupid, aren't they? Plus 1/3 x cubed. These examples in some sense almost too nice to really properly learn the long division, but it is what it is. I'm sorry, guys. 1/3 x cubed. And then 1/3 times 1/2 is what? 1/6, right? So we have minus 1/6 x to the 5th, and then stuff that's higher order, we don't care. Stop that. All right, and then we subtract, what do we get? So as we take the subtraction, we basically are up against 1/30th plus minus 1/30th plus 5/30ths, which is 4/30ths, which is 2/15ths. So we get 2/15ths x to the 5th plus dot 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 dot. So then the next thing up here is, of course, 2/15ths x to the 15th, right? So therefore, the power series for tangent, oh? Oh yeah, got a little carried away. Sorry about that. You know, x plus 1/3 x cubed plus 2/15ths x to the 5th plus dot 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 dot. Now, so there you go. That's the Maclaurin series for tangent to 5th order. Or in other words, it's the Maclaurin series for tangent, the first 3 non-trivial terms. Oftentimes I ask you guys for the first 3 non-trivial terms. Yeah? Now, could you do this with Taylor's theorem? Let's talk about that for a second. Could you do this directly by calculating the Maclaurin series from the Taylor's theorem? Sure, you could, right? Starts out easy enough. F of 0 is, well, if this is f of x, right? F of 0 is 0. F prime of 0 is what? Well, f prime of x is what? Secant squared x, yeah? Well, that's not too bad. F prime of 0 is 1. What's f prime prime of 0? Well, what's f prime prime of x? It's 2 secant x tangent x, plus, I feel like I did this already. My bad, guys. Oh, that's it, right? So that's 0. You see where this is going. I mean, you could do this. You could suffer through this. But man, this is much, much simpler as a method for finding the Taylor series at 0. Question? Yeah.
This might be slightly off topic. If you had f of x equals 1 take away x over cosine,
Uh-huh.
could you use reciprocals? So could you flip that upside down where 1 over f of x equals cosine.
Well, you
x.
could just do the long division, like just on this. You just have, you know,
Oh, I see.
1 minus x here, and you'd have like that.
I was thinking about using geometric.
Oh yeah, I mean there. Well, yeah, you could flip it. You could find yes, you could flip it, use the geometric series for the reciprocal. But then the bad news is that there's not a nice flip the series theorem. Like what I have done in the notes is derived the first 3 terms in the flip the series theorem, and you see that it's going to get more complicated as we go to higher orders, because that thing with the like terms combining is just going to get worse as we go to higher orders. Now, if you're curious, the notice at the top I've got the next term is 17 over 315 x to the 7th, right? Seriously? Sorry guys, so you know you've got, so I just for kicks I plugged it into Wolfram Alpha and poked it a bit, and here's the next 3 non-trivial terms in the power series for tangent. I don't see those being on the test, right? In fact, do I expect you to memorize the power series for tangent? I do not, but I do expect you to be able to derive it, or to work with it if I give it to you, all right? The ones I expect you to have memorized are exponential, sine, cosine, cosh, sinh, geometric, right? And you should also be ready to derive things with the geometric series like we have. We should do more of that. So here's the, for kicks, you know, what's the power series for hyperbolic tangent? Well, if you can do long division to get this, right? We could do that. This is 1 over cosine, so the next term past the one we've calculated is, wait a minute. Wait a minute, what? Oh yeah, we do have that 5 over. I was remembering, my examples are mixing. I was remembering 2/15 here. I'm thinking of the other example. But the next past that is 61 over 720. This one's kind of fun. If you want to find the power series for 5 over x squared plus 4x plus 5, you could do that. Right? Does anybody need to see me do one of these? I can do another one if you'd like.
If you 6.8.
6.8, yeah, I'll do that one. I think that one's a little bit different. Let's see here. Let's see here. So I've got, I want to find the Maclaurin series for 5 over x to the x squared plus 4x plus 5. All right, so so first of all, the first thing is important, and it seems kind of silly, but for me, this is the most important thing, is to write the series from lowest to highest order. What's the power series for the quadratic? It is the quadratic, you see? So this is 5 plus 4x plus x squared. And I don't need the plus dot 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 because that's it. This is the power series for that quadratic. And so how many times, so what do I start with? I start with 1. 1 times this gives me 5 plus 4x plus x squared. I subtract. I get minus 4x minus x squared. So what comes next? How can I get a minus 4x from this? I need minus 4 over 5 times x. And that will give me, when I multiply this by, that will give me a minus 4x minus 16 over 5x squared plus stuff. So I subtract. Let's see here. So I subtract the 4x, minus 4x's cancel, and I need to figure what is minus 1 plus 16/5. You guys are right. 11/5. So we get 11/5 x squared plus dot dot dot. So how do I get an 11/5 from multiplying by 5? I need seriously, minus 11 over 25 x squared, I think. That would give me 11/5 x squared plus dot 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 dot. And so plus 11 over 25? Oh yes, thank you. Plus 11 over 25. Yeah, I think it whatchamacallit, it sorry guys, I will eventually figure out the power settings on this computer.
It's not one of your students, it doesn't fear you yet.
It doesn't fear me yet? Yeah, it's, hey, come back to us. What? Well, I see it. Why isn't it? Hello? Hello? Well? Oh well. Happy convo to you all.